Okay, so before studying what will be the motion of these charged particles as they move to the poles, let's just review what the motion of a charged particle is in a uniform B field. Suppose we have a positive charge moving in this direction. What will be the direction of the force acting on it? Upward, so it will do such a circular motion. Well, treating this circular motion of this point charged particle as, on the average, as a current running over the trajectory, what will be the direction of the magnetic dipole moment? Well, there is a plus Q charge moving in this direction, so the current is running in the counterclockwise sense. Just curl your fingers. This will be the direction of the magnetic dipole moment of this system. What about a negative charge? Let's say I have a minus Q charge moving in that direction. Well, it will feel a downward force. V cross B is upward. Since the charge is negative, it feels a downward force. What is the direction of the magnetic dipole moment of this system? In the same direction. Negative charge is going in the clockwise sense, which on the average will correspond to a current in the counterclockwise sense, just like in the case of a positive charge. Well, the direction of the magnetic dipole is just take your loop, I, take your right hand. Curl your fingers in the direction of I, your thumb points in the direction of the magnetic dipole. In these two cases, the current is running counterclockwise sense. Take your right hand, curl your fingers in the direction of the current. So this is the direction of the magnetic dipole moment. If it's a negative charge, the thing that you have to pay attention to is that the direction of the current is not in the direction of the motion of the negative charge, but in the opposite direction. So since this is going in the clockwise sense, the current, the average current on this loop will be on the opposite sense. Well, you see, in both cases, whether the charges are positive or negative, the magnetic dipole moments are in the opposite direction of the B field. So let's see, we know that F is equal to the gradient of M dot B. Well, in this example of the charged particles in this one element belt, of course, the B is not uniform. But still, compared to the, taking into account the size of the Earth, and these dipoles are small, at their length scale, it's almost uniform, almost. And they will have an average magnetic dipole moment which will typically point in the opposite direction of the B field. So this will be equal to the gradient of minus MB. M and B being the magnitudes of the magnetic dipole moment and the B field. Well, treating the magnitude of the magnetic dipole moment to be more or less constant, so this is the force acting on our charged particle on the average. But you see, gradient of a function, a scalar function, is always in the direction in which it is increasing. So gradient of B is in the direction in which the B field is increasing. M is just a positive number. If you just multiply it with a minus sign, the force is in the direction in which the B is decreasing. The magnitude of B is decreasing. Well, let's see, the magnitude of B is increasing towards the poles. So the forces acting on these dipoles will be in the opposite direction, away from the poles. Okay, so let me repeat this. We have these point particles. Well, they are not current loops, but nevertheless, we can assume on the average that they form some loops. And corresponding to these loops, we can assign some magnetic dipole moment. And this magnetic dipole moment will be pointing in the opposite direction of the B field. Okay? So the forces are such that they will rotate in a way that the magnetic dipole moments will be in the opposite direction of the B field. If M and B, they are pointing in opposite directions, then their scalar product is nothing but the product of their magnitudes times -1. Well, this M is constant. Let's just take the -M out, so what remains is the gradient of B. Now, if you remember our lectures on the first weeks, we studied the gradient of functions, and we said that the gradient of a function is a vector that points in the direction in which that function increases. So this gradient of B is a vector pointing in the direction in which the magnitude of B is increasing. Well, I have this vector which points in the direction in which the magnitude of B is increasing, and I multiply it with a negative number. So this whole thing is a vector which points in the direction that the magnitude of B is decreasing. So the direction of the force will be in a direction in which the B will be decreasing. So we have this charged particle circling my loop, my magnetic B field lines. As it's approaching the poles, there will be a force acting, the non-uniformity is increasing in my B fields. So the force due to this non-uniformity will be towards the direction in which the B field is decreasing. The magnitude is decreasing, well, the magnitude is decreasing in this direction, away from the poles. So that's why as these charged objects move towards the poles, they will feel a force that will push them away from the poles.
Oradan biri kutuba gidiyor. Peki hiç çıkmıyor mu evrimlerin?
Well, of course, if they will be colliding with each other at some point. They will have their velocity might be pointing in the direction of the magnetic field line, so the magnetic forces will not be any. There won't be any magnetic force, etc. So they can lose their energy, etc. As they approach, they might collide with the atmosphere over here, lose their kinetic energy, lose their velocity. So they will be closer to the Earth. They will, of course, sooner or later leave that region, but most of them get trapped until they lose their energy. Well, they are dangerous when they have a large energy. If they lose their energy, they are not dangerous.
Durma olasılıkları var peki.
What happens to gravity? Gravity will always pull them. So even if at a given instant they stop, they will start moving. What will be their acceleration close to the Earth? They are so small, so light.
Sıfır. Kuzey ışıklarına mı diyorsun?
Now, we are talking about these charged objects. Let's say, suppose they stop at a given point, given time, close to Earth. So what will be their acceleration, subsequent acceleration, due to their weight? Their weight is negligible, right? Yeah. So what will be their acceleration?
Infinity. Sıfır değil.
So No, forget about modeling this. I have my question first. So I have these point objects that are so light. And your friend was asking what happened, will they ever stop? And I asked them, okay, let's assume for a time being that they stop. They come over here, they come very close to the surface of the Earth somehow, and at that point they stop. And of course their acceleration might be zero, might not be zero, I don't know. What will be their acceleration, do you know?
2 olur.
Yeah, 9.8 meters per second squared. 109. I don't care how light they are, their acceleration close to the surface of the Earth is always 9.8. Okay, the weight is almost negligible, but you don't divide the force by weight.
Yeah.
Also, that's another issue. Okay. Now, any questions on this? Let's do an example. On this one. Well, let's assume, just for simplicity, we have an atom. Just a very simple model. Around it, there's an electron orbiting it. Don't repeat this description in your quantum physics or quantum mechanics courses. Let's keep it classical. So what is the velocity? Let's say the orbit has a radius r. What will be the velocity? Well, it's doing uniform circular motion, so there has to be a force acting on it, which is given by mv squared over r. And at the same time, the only thing that can create this force is, let's say, the electrostatic force due to the nuclei. So and that force is 1 over 4 pi epsilon 0 z times e squared over r squared. Well, there is z times e at the center, e of the electron, or let's say v squared will be just 1 over 4 pi epsilon 0 z e squared over m times r. Now let's take this electron, let's take this atom and put it in a uniform magnetic field. What is the direction of the magnetic dipole moment? Let's say it is rotating in this sense. Magnetic dipole moment is into the screen. Now I pick up the same system, same atom, put it in a uniform magnetic field, let's say into the screen. Let's say its velocity now is v prime. And again, for simplicity, let's assume the radius of the orbit does not change. The radius is the same. Now what is the velocity? Since it's doing uniform circular motion, there should be a force, the total force acting on it should be equal to the centripetal force. Well, the forces acting on it is the electric force of the nuclei, which is again 1 over 4 pi epsilon 0 z e squared over m times, no, z e squared over r squared plus, what is the direction of the magnetic force? V prime cross B is towards the nuclei, but this is an electron. The force is away from the nucleus because the charge is negative. Minus QV prime B.
Why is there a minus?
What is the direction of the magnetic force? The magnetic force is QV cross B, right? So this is my V. B is into the screen. So V cross B is pointing towards the nucleus. But the charge of the electron is negative. So it is pushed out of the screen, away from the nucleus by the nuclear force. So that is why this is the force towards the nucleus, the component of the force in the direction of the nucleus. It has to be mv prime squared over r. This force is created by the electrostatic attraction, plus the force of the magnetic field. I'm just defining E to be a positive number. It's not the charge of the electron. The charge of the electron is minus E. So let's see, mv prime squared over r plus ev prime b. This should be equal to mv squared over r. Because you see this 1 over 4 pi epsilon 0 z e squared over r squared is just mv squared over r. V being this, its v squared being its speed squared in the absence of the B field. Which one is larger, V or V prime?
V.
Yeah, V is larger because V squared is V prime squared plus some positive number. So V is larger than V prime. Hence, this electron has slowed down. The magnitude of the magnetic dipole moment is reduced. Remember, it was into the screen, and then when we put this atom in a magnetic field, it is still into the screen but with a smaller magnitude. So basically, the magnetic dipole moment of this system has increased in the opposite direction of the B field. You see, initially, this is the magnetic dipole moment. So when we add the B field, this is the magnetic dipole moment. Let's call it M prime. The change in the magnetic dipole moment is this one. So this is the direction of B. So delta M is opposing the B field. Well, here I made a simple assumption that the radius of the orbit stays constant. And as far as I know, it does stay constant. Now, why does the speed change? We will study it later on. I mean, we will come to that. So basically, I'm just trying to motivate the fact that if you have an atom, put it in a magnetic field, its magnetic dipole moment will increase in the direction opposing the magnetic field. So that's the main lesson that I would like to derive from this discussion. So now we have two mechanisms which basically change the magnetic dipole moment of an atom. One mechanism is that if the atom already has a magnetic dipole moment, it will just rotate so that its magnetic dipole moment points in the direction of the B field. Or put it in a different way, the change in the magnetic dipole moment of the atom, when you place it in a magnetic field, will be in the direction of the B field, if the atom has a permanent dipole moment. Now, we have also seen this other mechanism. Let's suppose that the atom has all these electrons, and somehow their magnetic dipole moments will cancel each other. Now, when we put this system in a magnetic field, then the magnetic dipole moment of each one of the individual electrons will change in the direction opposite of the magnetic field. Original magnetic dipole moments, they summed up to give 0. When we add this change, all of this change will be in the opposite direction of B. I will have a net dipole moment in the opposite direction of B. Just you can think of it as, if you just compare it with the electrostatic analog, we had these atoms which had dipole moments, electric dipole moments, or molecules that have electric dipole moments. And when we put them in an electric field, they just rotated to align themselves with the external electric field. The same phenomena happens over here. If we have atoms or molecules that have a permanent magnetic dipole moment, when you put them in a magnetic field, they will align themselves so that their magnetic dipole moment will point in the direction of the applied B field. So it's almost exactly the same phenomena. Then there is the induced electric dipole moment phenomena. We said that, okay, if you have this, let's say, a single atom which doesn't have a permanent electric dipole moment, when you put it in an electric field, the charges will be displaced such that there will be a dipole moment induced on the atom, and this new dipole moment will also point in the direction of the electric field in electrostatics. Now there is an analog phenomena here. If you have a system which doesn't have a magnetic dipole moment, you put this in a magnetic field, and putting it in a magnetic field will create a magnetic dipole moment. But this time, this magnetic dipole moment will be pointing in the opposite direction to the magnetic field. In the case of electrostatics, the induced electric dipole moments pointed in the direction of the electric field. In magnetostatics, these induced magnetic dipole moments will be pointing in the opposite direction of the electric field. Now, how does this velocity change as we put this in a magnetic field? As I said, we will discuss it later on.
Yani hocam atomun çevresindeki elektronları durdurabilir miyiz bu yolda?
Well, most probably, after some point, if you increase the magnetic field, the atom will flip its direction. I mean, it's not so easy to stop the electrons. You are creating a magnetic dipole moment which will try to align with the magnetic field.
Zeeman effect bununla alakalı mı?
No. You see, just keep a moment. Now, the magnetic field, the induced magnetic dipole moment, let's say the average, on the average, it will be in the direction of the B field multiplied with some constant. Let's call it the magnetic susceptibility. Now, the cases are, this can be positive. So this is what we call diamagnetism. Well, it's just like the dielectrics. So you have a magnetic dipole moment induced in the direction of, so let me call this molecular. Magnetic dipole moment induced in the direction of the magnetic field, just like electric dipole moment in the direction of the applied electric field. It can also be negative. This is what we call paramagnetism. So we can have diamagnetic material, paramagnetic materials. Well, most of the time, in fact, in reality, in all materials, we have both of the phenomena. But diamagnetism is much stronger than paramagnetism. So if you have a system which has a permanent dipole moment, then that material will be a diamagnetic material. If it is made up of molecules that don't have a permanent dipole moment, then it will be a paramagnetic material. Yes?
Why is the force in the absence of magnetic field is equal to the force after a change?
They are not. You see, this is the force in the absence of the magnetic field. This is the force in the presence of the magnetic field. They are not equal.
But here, we want
No, I didn't. No. What I said was 1 over 4 pi epsilon 0 z e squared over r squared, that piece only, is equal to this one.
yes.
That's the only thing I used.
Hocam şimdi elektrondan dolayı bu manyetik dipol oluşuyor ya. Çekirdeğin üstünde oluşuyor dipol. Protonlar o zaman bir
I mean, you see, the dipole is a large object. It's not a point object. You cannot say that the magnetic dipole moment is at this point. But we always idealize saying that the atom is a point object. If the atom is a point, its magnetic dipole is at that point. Only in that sense, the electric dipole, magnetic dipole is at a point. But since the atom is a point itself, you cannot say that, oh, the electron is over here, the nuclei is over there. So you can talk about a magnetic dipole moment only if you are sufficiently away from the dipole, so that you cannot see what is inside. It just looks like a point. Now this we will discuss in more detail later on. Now any questions up to this point? So the idea is that if you have a material, the applied B field will be modified due to these magnetic dipoles. Either they will contribute in the same direction of the applied B field or in the opposite direction, but they will modify it.
Hocam manyetik alanı tam tersine uygulasaydık o zaman elektron hızlandırmış mı hocam?
Yes.
Ne kadar? Nereye kadar?
Calculated.
radar tutuyor.
Hmm?
Radar tutarsak ölçeriz.
Put some numbers and see how much you can increase the velocity.
Yani işin kafama gelemez zaten. Kafama da gelemez. Ama yapın.
Put some numbers. I mean, you see, for an hydrogen atom, we know what the radius of the atoms are. We know the radius. We know Z. We know E. You know everything. So you can determine their speed in the absence of a magnetic field. So you can determine the right-hand side. Now the crucial thing is, how big can this be? The largest magnetic field that we could generate on Earth is something like a couple of 10 Teslas, let's say. Not much, not larger. On the surface of the Earth, the magnetic field is typically like 1 Gauss. Well, 1 Tesla is 10,000 Gauss. So we could create 10 to the 5 times the magnetic field on the surface of the Earth. Just put in numbers and see how big the second term is, so that you can get an idea of how much you can change the velocity or the speed.
Hocam bir şey sorayım. Bu kuvveti yazdık ya işte.
Hı hı.
M.B. Orada yani manyetik dipol ya bir nokta evet. Şimdi bir nokta var. O noktadan çıkan manyetik dipol var. O manyetik dipolden dolayı mı kuvvet hissediyor o nokta?
Yes.
Bir şey de söyleyeyim mi? Hani en fazla 10 Tesla dediniz ya. Böyle yapıldığı şey. Daha fazlasını üretirsek dünyanın yüzeyi böyle kalkar mıydı?
Put in the numbers. And then you can decide on your own. How much current do you need to create 1 Tesla in a solenoid, let's say? Put in the numbers. Other questions? In your final, you will probably need your calculator. Okay. Now you remember that the vector potential created by a magnetic dipole away from it is m cross r over r cubed, mu 0 over 4 pi. This is our material. So let's try to calculate, this is our point r, the vector potential at the point r. Well, it might be that we put some currents running through our system, and those currents will contribute to this vector potential. And we already know that their contribution can be written in this form. But furthermore, it's possible that these currents, the magnetic fields created by these currents, create magnetic dipole moments or change the magnetic dipole moments of our system. They align them, they create them. And these additional magnetic dipole moments will also contribute to my vector potential. So let's say that if we take a volume over here, that volume will have some magnetic dipole moment. So this is the total magnetic dipole moment. Let's define a magnetic dipole moment density as this should be m times delta v, or delta v prime, let's say. So the contribution due to that magnetic dipole moment will be mu 0 over 4 pi m at the point r prime cross r minus r prime divided by r minus r prime cube dv prime. Of course, I have to sum the contributions of all of them, which is nothing but my integral. Now, just a warning. We always keep writing the vector potential in this form. But keep in mind that here, our magnetic dipole is, let's say, at a given point. This vector r is and we want to calculate the vector potential, let's say, at this point. This vector r is the position of that point relative to my magnetic dipole moment, not relative to the origin. Or you can say that you choose your origin at the position of the magnetic dipole. In that case, r is the position of your observation point. But in general, r is the relative position of your observation point relative to your magnetic dipole. So that is why here I have these differences, r minus r prime. R prime is the position of my magnetic dipole. R is my observation point. So the relative position of my observation point relative to the dipole moment is this r minus r prime. Now this m is what we call the magnetization. So the system becomes a magnet. Now let us try to simplify that last term. You see, what I will try to show is that, well, this is a term that we are familiar with. If there is a current divided by r minus r prime, integrate over the volume, gives you the contribution to the vector potential. I will try to write this term as something divided by r minus r prime. So that's something I can describe as kind of an effective current density. Just like, if you remember our discussion in electrostatics, we said that, okay, you can polarize a medium by applying an electric field either by an external charges or the charges you put in your system. You polarize it, and the polarization can effectively be described as some bound charge distribution. So that is what we will do over here also. So we will claim that magnetization will behave basically like a bound current distribution. So that will be the purpose. Now let's start with this vector product. But this is nothing but r prime cross the gradient prime with respect to, the gradient is with respect to the coordinates of r prime of 1 over r minus r prime. Well, this will be almost, well, this will be equal to minus the curl with respect to the primed coordinates of m of r prime divided by r minus r prime. And then the curl of m of r prime divided by 1 over r minus r prime. What is the relative sign?
Plus.
Plus. Let's check. Let's be sure. Let me calculate this one. Curl of m of r prime times f of r minus f of r minus r prime. F is my 1 over r minus r prime. Let me calculate the I component. Now the I component is epsilon ijk del over del xj prime mk r prime times f. This is equal to epsilon ijk derivative of mk prime with respect to xj prime f plus mk prime times derivative of f with respect to xj prime. This is equal to curl of m, the I component multiplied by f, epsilon ijk times this derivative just gives me the curl of m, the I component of m, plus epsilon I or minus epsilon I kj mk prime del f over del xj prime. Why minus? Because I just exchanged the positions of k and j. So this became minus epsilon I kj. So curl of m prime f, the I component, is the curl of m, the I component of f minus m prime cross the gradient of f, the I component. So this is my vector identity. Now, in the above, I have m cross the gradient of 1 over r minus r prime. Now, these are with respect to the primed coordinates. This is equal to curl of m prime multiplied with f minus the curl of m prime times f. So it's plus. Now I will just substitute this into my integral expression. So I remember I have m r prime cross r minus r prime over r minus r prime cube integrated over the volume. This is equal to minus the curl of M at R prime multiplied with F integrated over the volume plus curl of M at the point R prime. Sorry, this F is 1 over R minus R prime. Times 1 over R minus R prime over my volume. Okay, now let's look at this one. Here I have the integral of a total derivative. I can convert it into a surface integral. That will be equal to M of R prime over R minus R prime cross dA
S desek olmaz mı?
ds plus curl of M of R prime over R minus R prime.
Baştaki eksi mi dedi?
Well, that minus sign now when I convert that, if you want that minus sign, it is this one. So the problem is which way you put the area vector to take that cross product. It changes the sign. So what we ended up having A at the point R. We have these two contributions. One from the current running in our system. Then there's an additional piece coming from the magnetization of our system. Well, here in this last term, I just substituted ds is equal to n, the normal vector. The area vector is in the direction of the normal vector, multiplied with ds, the magnitude. So you see the effect of magnetization. These are these two terms. And they just look like this term. You have a current density divided by the distance from the observation point, summed over all the points that you have. One is a volume current density. So J bound is just at the point R is the curl of M at the point R. And then we have this surface current density at the surface. This bound surface current density, which is M of R curl dN. Now, again, compared to with the electrostatics, we had seen that if when you put your medium in an external electric field, or you put some charges, they polarize the medium. The polarization behaves like a bound volume charge density given by the divergence of the polarization. And there was also a surface charge density given by the normal component of the polarization. Well, this is basically in a sense similar to that, but in this case the current density is given by the curl of the magnetization, and the surface density is given by the component not perpendicular to the surface, but the parallel component of the magnetization. The normal component of magnetization doesn't contribute to this product. It's only the horizontal component of magnetization that contributes to our surface current. Now let's see where these come from. Let's assume we have our material. It is magnetized out of the screen. You see, this magnetization, we can just treat it as, we said that this magnetization is due to these electrons orbiting the atoms mainly. So we can just treat each one of these atoms as very small loops, very small loop currents. So there is a loop current running in this direction. There is a loop current running in this direction. Etc. So they are either aligned by the external magnetic field, or they are created by the external magnetic field, so that our system is polarized. Now, if you look at this point over here, in one loop, I have a current running in this direction. On the other loop, I have a current running in the opposite direction. So on the average, at that point, if both of these loops carry the same current, I don't have any current inside. Well, if the magnetization is not uniform, then one loop will carry larger current than the other one. So I end up having a current running either one way or the other way horizontally. I will obtain a horizontal current at that point. So if M is not uniform, that is given by the curl of M. If you look at the surface, you see, at this point, well, the only current running is in this direction. At this point, there's only a current running in this direction. So effectively, on the surface, there's a current running in this direction. Well, M is out of the screen. This is the direction of N. M cross N is in that direction. So M is, that's why we have this M cross N over here. So the magnetization basically behaves as if there is a surface current density. And if it is not uniform, there will also be an internal current density. So for example, if you pick up a magnet, of course there is no current running through it. No charge is moving from one point to the other point. But effectively, at every point, there is some current, some circular current created by these electrons orbiting their nuclei. So your bar magnet is basically just a prism, rectangular prism with some surface current running around it. Now that's a magnet. That's a magnetized material. Effectively, it behaves as if there is a current running on the surface. Of course, there is no free current. The charges are not going from one end of their magnet to the other end unless you connect it to a battery. But effectively, the magnetization can be described as if there is this effective current running around it.
Şu içte böyle ters yönlü oldular ya, cancel mi ediyorlar dedik onu?
Yes. Well, you see, how do you define the current? You just count the charges moving in one direction, subtract the charges moving in the opposite direction.
O zaman bu hani bound volume current'tan nasıl bahsediyoruz?
Well, they will cancel exactly if magnetization is uniform. Well, if magnetization is uniform, the curl is zero. If magnetization is not uniform, then they will not exactly cancel each other. There will be some residual current also inside.
O zaman hocam bir mıknatısın yanına metal bir şey koyduğumuzda çekiyor ya. Ondan bu şekilde.
Well, what I'm saying is you can describe your magnet as if there is a current. So why do two magnets attract each other? You have one magnet over here. It will create a B field. There's another magnet over here. So it will feel this force. This is the B created by the other magnet. This is the magnetic dipole moment of your initial magnet, the magnet that feels the force. So from this law, you can calculate. How do you calculate the B? Well, you can treat your initial magnet as if there's a current running around it. Calculate the magnetic field it creates over here. Multiply it with the magnetic dipole moment of this one. Take the gradient, that will give you the force.
Hocam şurada M dedik ya. Bunu total magnetic dipole diyebilir miyiz?
M is the magnetic dipole density. You see, M at a given point, at the point R, is defined as you just take your volume at the point R. Let's say this is delta V. It has a total magnetic dipole moment delta M. So M at the point R is delta M over delta V. This is how we defined it.
John, what's the exact physical meaning of effective environment? Because we hear...
Well, effective basically tells you that it's not actually true, but you can describe it as if it is true. It behaves exactly the same way as if it was true. So you see, if you just, for example, cut a hole in your magnet, connect a light bulb, a LED, between those two edges, there won't be a current running through your LED. There won't be light coming out. So there's no current there. No charge is moving from one point to the other point. But effectively, it behaves as if there is a charge moving. Because if you could actually look microscopically at every point, you will, on the average, see the charges moving in this way. But of course, it will not be the same charge. At this point, you will see as if the charge is moving that way, but it is doing this circular motion. If you look at the next point, you will see another charge moving that way, but it's doing this circular motion. Those two charges will not be the same charge. They will not move from one point to the other point. But when you look at there, if you can, you will see the charges moving in this direction. Other questions? So see you on Tuesday.